You know, it's funny. We talk about AI being everywhere now, doing these things that seem almost magical, right?
Yeah.
And today's deep dive is about one of those moments, like when one of those magical things became possible image recognition. We take it for granted now, but
Oh, for sure.
it's wild to think how recent this all is.
Yeah, it really is. I mean, even just a few years back, the idea of a computer actually seeing, like we do, understanding an image, that was like the holy grail of computer science, a huge challenge.
Exactly. And we're going to unpack this one research paper. It's from 2012. The title's mouthful. ImageNet Classification with Deep Convolutional Neural Networks. Catchy, right?
Right.
But it was a turning point, seriously, like handing scientists the Rosetta Stone for computer vision.
It's one of those papers that sends ripples through the whole field, you know?
Hmm.
And to really get why, we have to go back to the problem itself, the thing they were trying to solve, which, honestly, it's kind of funny how hard it is when you think about it. Teaching a computer to tell the difference between not 10 things, not 100, thousands upon thousands of objects.
So, like, teaching a computer what cat means, but times a million.
Exactly.
Because it's not just one cat, right? It's every breed, every position a cat could contort itself into.
Wait.
A cat hiding behind a couch.
Right, right.
Partially obscured.
All the cats.
All the cats. So why was that scale, that huge amount of data, so important?
Well, it goes back to how learning works.
Right.
For anything, really, whether you're a computer or a human. Think about a kid, how they learn. You wouldn't show them one photo of a cat, and suddenly they've got the concept down.
Right.
They see cats everywhere,
Way.
in every situation.
Mm-hmm.
A fluffy kitten, a grumpy old cat.
Yeah.
Machines need that same kind of exposure, tons of data, to generalize, to actually learn what they're seeing.
Okay, so before this paper, this whole ImageNet thing, were researchers basically working with, like, a shoebox full of cat photos? What was the big change?
Pretty much. I mean, the data sets were small, so you can imagine the limitation to be like trying to learn a language, but you only had a handful of words to work with.
Right.
You'd never be fluent, would you?
Not very well.
ImageNet, that was the game changer. Huge data set, over 15 million images, all meticulously categorized. They had something like 22,000 different categories.
So not a shoebox, but a whole library of cat photos, plus every other object you could imagine. But it's not just the sheer number, is it? It's the messiness, the real-world chaos of those images. That seems important, too.
Absolutely. That's key, actually. You've hit the nail on the head. See, one of the biggest hurdles in object recognition is this. Teaching a computer that a cat is still a cat, even if it's at a weird angle, half hidden by a blanket,
Right.
different lighting, whatever. ImageNet had that vastness, that real-world variability. That's what made it so valuable. It was training AI to see the world, well, more like we do.
Okay, so we've got mountains of data, millions of images of cats being cats and everything else under the sun. But how do you even start to build a computer brain that can actually make sense of it all? That's where these convolutional neural networks come in, right? CNNs?
Yeah, CNNs. They sound really complex, like something out of Star Trek.
Right.
But they're actually really elegant in a way, because they're modeled after how our own brains work.
Hold on, are you saying my brain is already a CNN Pro? Because I can barely remember where I put my coffee, let alone...
Well, maybe not quite.
Okay, good.
But think about it, right? How we process what we see. We don't see the world as just a jumble of pixels, right?
Right.
Our brains, they break down an image into these layers of information. So you see edges first, then shapes.
Yeah.
And your brain pieces it all together. And eventually you recognize, oh, hey, there's a cat.
Right.
CNNs, they work in a surprisingly similar way. Each layer in the network, it learns to recognize more and more complex features.
So it's like each layer builds on the one before it. So first, it's just seeing lines and edges. But by the end, it's putting those pieces together and going, aha, that's definitely Mittens creating chaos on the bookshelf.
Yeah, exactly. It's like the early layers, they're the
Yeah.
foundation. They detect those really simple features, right?
Yeah.
And then as you go deeper into the network, those layers, they start to recognize more intricate patterns. And it's this hierarchical approach, this building up of understanding,
Yeah.
that's what makes CNN so powerful for images, especially compared to the older ways of doing it.
So we've got this incredible tool, CNNs, and we've got this massive data set, ImageNet. But I can't help but think, to run all of this, you must need some crazy supercomputer, right?
You might be surprised to hear this, but
Yeah.
this paper, one of the things they highlighted was actually the role of something a little more common, especially for any gamers listening. Powerful GPUs.
Wait, you're telling me my gaming PC has something in common with groundbreaking AI research? I knew those late-night gaming sessions were building valuable skills.
In a way, yeah. See, GPUs are amazing at parallel processing.
Right.
It's what lets them render those complex graphics in games, right?
Yeah.
Turns out that's perfect for the kind of massive calculations that CNNs need. It was like finding the missing piece of the puzzle.
So it's not just about having the data, not just about having the right algorithms.
Right.
Even the hardware itself plays a key role.
Huge role.
But something tells me there's more to the story, right? Like, it can't be as simple as, here's a pile of data, go wild, supercomputer. There's got to be something else.
You're absolutely right. The paper's full of these really clever techniques, almost like shortcuts or hacks, but in a good way.
Efficiency hacks.
Exactly. Like little tweaks that they made that ended up making a huge difference in how they train these networks.
Okay, now you've got me really curious. Give me an example. What kind of efficiency hack are we talking about here? Okay, give me the inside scoop on these efficiency hacks. What were these researchers doing to supercharge their AI training?
So one of the really ingenious things they did is called data augmentation.
Okay.
And the idea is this. Imagine you're trying to teach a kid what a bicycle is, right?
Okay.
But you only ever show them pictures from the same angle.
Right.
Same color, same everything. Chances are, if they see a red bike instead of a blue bike, or a bike with a basket on it,
Right.
they might get confused, right?
Yeah.
They need to see all the variations, all the different ways a bike can be a bike.
To really get the concept.
Exactly. And that's what these researchers did. They took their data set and they basically gave it superpowers.
How so?
They created all these slightly altered copies of the images,
Okay.
like flipping them, cropping them, even messing with the colors a little, the brightness.
So it's like showing the network a photo of a cat, lounging in a sunbeam, and then the same cat but a little darker, like it's wandered into the shade.
Exactly.
And the network learns, okay, different lighting, still the same cat. That's so smart.
Right. Makes it more adaptable, less reliant on those really superficial details.
I love that.
And then there's this other technique. It's called dropout, which, I don't know, sounds a little harsh.
Dropout. Okay, yeah, you're going to have to explain that one. That sounds like something out of, like, a robot gladiator movie, not an AI paper.
Right. But it's actually very clever. Imagine this. You're building this complex machine, and you want to make sure every part is essential, right?
Okay.
So you might try removing a part here, a part there, just to see, okay, can it still function without this?
Yeah.
That's the basic idea behind dropout. During training, they would randomly turn off certain neurons in the network.
So, like, literally hitting the off switch on parts of the AI's brain temporarily, I'm guessing.
Yeah, and it seems counterintuitive, but
Why? Why would you do that?
it forces the network to adapt.
Yeah.
Because suddenly it's got to find these alternative pathways
Yeah.
to solve the problem. It's like if you have a team and you force them to work together, even when some members are unavailable,
Yeah.
prevents them from relying too much on any one person.
So instead of just memorizing the data set, it's like you're forcing the network to really understand the underlying features that make an object what it is.
That's exactly it. Dropout. It helps prevent something called overfitting. That's when the network gets really good at recognizing the specific examples it's seen, but
Because it can't generalize to new things.
exactly.
Gotcha.
So you put all these things together, right? These techniques, the huge ImageNet data set, the power of CNNs, and it led to some pretty incredible results.
Drumroll. Did it work?
It worked amazingly well. They achieved record-breaking accuracy on ImageNet. Like blew all the previous attempts out of the water.
Give me the numbers. How much better are we talking?
So one of the ways they measured it was the top 5 error rate, meaning like the network makes its 5 best guesses for what's in an image. How often was the right answer not in those top 5?
Okay, yeah.
This paper got it down to just 17%.
So 83% of the time, across thousands of categories, it was confident the right answer was in its top 5. That's incredible.
It was a huge leap.
But this wasn't just about winning a competition, right? This changed things. What was the impact?
This paper is foundational, honestly. I mean, so much of the image recognition we use every single day, it traces back to this research. The facial recognition that unlocks your phone, the image search you use to find that perfect picture, it all has roots in this paper.
It's wild how much we take that for granted now.
Right.
It's just like part of life. But it's all built on this research, these breakthroughs, and it's still influencing things, isn't it? Like researchers are still building on this.
Absolutely. This paper is like a landmark on the map of AI research. People are constantly citing it, using its insights to push the boundaries even further.
It's amazing though, right? how one paper can have that kind of ripple effect. But that's the beauty of a deep dive, uncovering these moments, these turning points that really shifted the course of technology.
For sure.
And speaking of shifting the course, you remember how the paper ended? They mentioned applying this to video next.
Oh, yeah. That was a pretty mind-blowing moment when I first read that.
Right, because it's one thing to look at a still image and be like, yep, that's a cat. But video, that's a whole other level. Suddenly, the computer's not just seeing, it's understanding a sequence of events, right?
Right.
Identifying objects, sure, but also movements, maybe even emotions. Eventually, it's like...
It changes everything.
It does. It's like teaching machines not just to see, but to truly, deeply comprehend what they're seeing. And that's a future I'm both ridiculously excited for and slightly terrified of in equal measure.
I hear you.
But hey, that's AI for you, right? It's the ultimate double-edged sword. Anyway, that's our deep dive for today. Make sure to check out the show notes for links to this incredible research and more. Until next time.